Good evening, sir. My name is Puneet Priyadarshi, and today I am going to explain the practice report 3, which is to explain the Grashof Criterion. So, what is Grashof Criterion? Sir, in layman terms, basically what it means is that suppose you have bars and you have a linkage between them. So, what this criteria helps us understand is to get an idea whether how much one part can rotate freely. So this is what is Grashof criteria, sir. And this lab report is committed, sir, to understand and analyze the Grashof criterion of 4-bar mechanism, sir. Now let's go to the next part, sir, which is analysis. And what this analysis means is predicting whether a part can rotate freely or not. So we start by making the frame, sir, and we denote the shortest part as S, and the part we choose as the shortest part does not alter the following analysis. So below also I have also attached some images. So let's go down. So there can be positions of the linkages and the bars. So the first position is the stretched position, which is the triangle one, or triangle inequality theorem. So according to which, what it means is that the sum of two sides of the triangle should be always greater than or equal to the third side. So this is what like in the stretch position, this is what is happening. In the second position, we have the overlapping position, which gives us two inequalities. The first inequality can be when Q is greater than or equal to P plus L minus N. And so if we were to increase Q, then for it to happen, then P rotates clockwise to become horizontal, as you can see in the figure. If we rotate Q, if we increase the length of Q, then P also has to rotate clockwise to become horizontal. In the figure, I think it's self-explanatory, sir. Now let's come to the Grashof criterion. So from the figures above, we can clearly notice that the conditions for the rotation of one of the linkages is only satisfied when S plus L is equal to P is less than equal to P plus Q, and condition 2 when S plus P is less than equal to Q plus L, and when S plus Q less than L plus P. So we can derive the same conditions if we move Q, that is adjacent to S, to the other side of the mechanism also. So now let's like this we have done the flow. And so in this whole report, what we will be proving, or what we will be seeing in the GIM software, is L plus S should always be less than equal to P plus Q, so that the Grashof criterion is satisfied. And basically what we have to do is that if this condition is satisfied, then it means that the free rotation of the linkage will be possible, and if it is not, then it is not possible, sir. So and if L plus S is greater than P plus Q, then it's a non-Grashof condition. And sir, there are two special cases also. The first case is the parallelogram case, and the second case is the kite case, sir. So generally, sir, if Grashof criterion is met, the parts other than the shortest can only oscillate with respect to each other. Like they have the oscillating degree of freedom. And if two parts can make a complete rotation, the two parts must be shortest at the same time. Therefore, and this is only true if two of the Grashof criterions are met. We can only get this using a kite or a parallelogram. So below also I have explained them, sir. As you can see, Grashof criterion mechanism. The first one is the double crank one. So in this, the shortest part is the frame, the base part. This should be equal to, if this condition is there, then the linkage is a double crank, also called a drag line. Both parts that are joined to the base line will rotate fully, sir. In the second condition, we have the Grashof crank rocker. In this, the shortest part is joined to the frame, the base part, and then the linkage is the crank rocker, sir. This is the most common 4-bar mechanism, sir. And the third one is the double rocker with rotating coupler. In this, the shortest part is the coupler, and then the linkage is a double. Like if this condition is satisfied, the shortest part is the coupler, then the linkage is a double rocker, sir. Now we have, as I told you above, that there are two special cases also. The first one is the parallelogram or anti-parallelogram case. So here the length of the shortest links are equal and the longest links are also equal, sir, if these conditions are satisfied. And also like the shortest and the longest, other two shortest and longest should be equal to the other shortest parallel longest. So if these three conditions are satisfied, sir, then we move into this case, sir. Now, coming to the second special case, we have the kite or the deltoid, sir. Here the length of the shortest links are equal and the longest links are also equal. So the difference between this is that the parallel sides, basically, if you consider that whole 4-bar mechanism as quadrilateral, so here the longest links are equal, shortest are equal, and the shortest and longest parts are adjacent to one another, sir. In the parallelogram, they were opposite to one another, sir. But here they are adjacent. So this is basically the difference between the kite and the parallelogram case, sir. Now, sir, let's jump into the RRR Grashof criterion, sir. As discussed above, sir, like for a 4R mechanism to have like at least one crank to rotate freely, it must satisfy P plus Q should be greater than or equal to S plus L, sir. So let's go in the figure. So, sir, this is the rough sketch which I could find online, sir. Like here, as you can see, this S denotes the shortest part, and P, Q, and L is there. So this, here, sir, as we have written, like P plus Q, this length should be always greater than or equal to L plus L. So, and only after this condition is met, Grashof criterion will be satisfied, sir. Now, sir, like we can create some geometry using the GIM software and verify the Grashof law. So in the example one, sir, we have drawn a 4-bar mechanism RRR with link lengths as follows. Length of link 1 is equal to 3 meter, link 2 to link 3 3.6055, and length of link 4 is equal to 4 meters, sir. And also the order of links are taken in clockwise direction in below figure. Yes, sir. Sir, as you can see, so I was a bit confused on whether I had to like show you, like give the video presentation of this whole working. So I just I'm just explaining you the figure of what I have done, sir. So if video is required, sir, then I can also put that too. So, sir, let's come back to this. Then here is the RRR mechanism, sir. So as you can see, these dotted lines, it depicts the trajectory, sir. Like these dotted lines, they depict the trajectory. In the GIM software, we just put in the lengths of the 4 cranks, and this whole here depicts the trajectory of this complete link, and this trajectory depicts the movement of this bigger link one. And so let's verify, sir. As we have already seen, sir, that S plus L should always be less than or equal to P plus Q. Then and then the data which I have entered here, this thing here, here it is coming 6 should be less than or equal to 6.6055, which is true. Therefore, for the Grashof law is satisfied for the above mechanism, and it must at least have one crank in itself. Like we can also observe from the figure that the shortest link here, this acts like a crank for the whole complete bar linkages, sir. In example 2, I have kept this following things, sir. Link 1, link 2, link 3, link 4, sir. And this RRR mechanism does not satisfy. Why? It's because 11 is not less than or equal to 9. This is why this condition is not satisfied, sir. I think I have miswrote a few things, sir. Like I have left the greater than sign here, sir. So sorry for that, sir. Now, sir, these things this verification is done in the GIM software. This whole thing comes as a video, sir. Like this will be rotating in the GIM software itself. So I was a bit confused on whether to do that or not. So I just did this trajectory and just showed it to you, sir. Now let's go back to the RRRP Grashof criterion, sir. Now we can derive the Grashof law for RRR configuration from the RRRP configuration from the above discussed RRR Grashof law, sir. So as you can see, what we are doing, sir, is like we are changing the 4 R's to 3 R1P, sir. And for doing that, we simply don't have to do anything. We just have to in the above figures, the two diagrams are equivalent. When we increase the XED link length and rocker length to the into infinity, then the mechanism looks like in third diagram in the figure 4, sir. This one, this whole thing, sir. Now, sir, let the length of the short links be L minimum, length of longest is equal to 1, XED link P is equal to 1, let the length of connecting rod is equal to L. Then from the Grashof law, this condition has to be satisfied. And as we can see, although both L and Q are infinity in length, but their difference is a real value, and we call that as offset, sir. So we can see in the third diagram, S plus E, this whole thing is satisfied also. Now let's go to the examples. Okay, so here like we have drawn the RRRP configuration with the following geometry, sir. The length of offset is equal to 0, length of connecting rod is equal to 447, and crank is equal to 282, sir. So Grashof law criteria for RRRP is equal to this S plus E should be equal to like wait, sir, I can sorry for the pause, sir. I made the few changes because my typing was a bit wrong, sir. So here, sir, as we can see, for the RRR P configuration, sir, we have kept these things, and as we can see that in the above figure, S plus E should be less than equal to P, sir. So equation 6 is the Grashof law for RRRP 4-bar mechanism, sir. And let me go to the figure, sir. Example. Okay, sir. So we will back to example. So Grashof law is simple, sir. S plus E should be equal to less than equal to P. So simply we just fill in the data, and from equation 9 we can see that a Grashof law is satisfied. And if okay, sir, like 1 second, sir. I am trying to focus, sir, on the this part. I think it's not focused. Okay, sir. So this GIM, using the GIM software, we can also verify this, like these dots that depict the trajectory of the whole body. So using this we can do that. Now let's go to example number 2, sir. Now we have drawn the RRP configuration with the following geometry, where length of offset is equal to 0, length of connecting rod P, and the length of crank is equal to this much, sir. So when we like if we you simply just remember the Grashof criterion, then this here is not satisfied. Also we can see the RRP mechanism that satisfied the Grashof law. So this thing will not like from this it is perfectly clear that if we put this following things as our configuration for RRRP thing in the then our we will not have a degree of freedom, sir, because Grashof law should be satisfied so that at least one thing should have a degree of freedom. Now let's go to the fourth part, sir. Here we are talking about RRPP Grashof criterion. Now here we can see this RRRP mechanism, sir. So when we extend the link 2 and link 4 to infinite length, and the length of link 3 also extends to infinity, sir. So from Grashof law, we can see that S plus L should be greater than equal to P plus Q, and also LPQ tends to infinity. Then Grashof law becomes S plus infinity less than equal to N plus infinity. So infinity. So we cannot compare infinity, sir. Both sides have infinity. So the RRPP chain is always a Grashof mechanism, sir, because of this law, sir. So now let's go to the Oldham's coupling, sir. Sir, so the best example for above RRP configuration is Oldham's coupling. It is used to connect two parallel shafts whose axes are at small distance apart. It is shown in the figure, sir, as you can see in the figure, sir. Sir, I actually made a tiny mistake, sir. Here S plus infinity should always be less than equal to infinity plus infinity. So this here we have two infinities, and here only one. So this left side will always be less than equal to infinity plus infinity. So that's why he always RRPP is always a Grashof mechanism. And now let's come back to RP. So it's very simple, sir. Again, we extend this link to infinity. Then link 3, this here, this also has to be extended to infinity, then only we can get this configuration. So as we can see, infinity plus infinity less than equal to infinity plus infinity. So we cannot compare this because of like clear mathematics said, like we cannot compare two infinities because both sides have that. So we cannot tell which is bigger, which is smaller. So that's why this is this RP chain is always said to be a non-Grashof cell. Yes. Now let's come to the Davis example. Davis steering mechanism, sir. The best example of RP chain is the Davis steering mechanism. So I have also and like given some photos, sir. Okay, sir. Okay, sir. So that's all from my side. So let me give a summary. So in this whole report, what we are trying to prove, we are trying to verify the Grashof criterion. What is Grashof criterion? It's very simple. If for a four linkage mechanism, for a 4-bar mechanism, Grashof criterion is useful for seeing or verifying if at least one, like if at least we have one successful crank, or that, or this means that at least one of our bars is like has a rotational aspect to it. So this is what we try to do here with the Grashof Criterion, sir. Sir, hope I was clear, sir. And regarding the videos also, like I did not know, like I had to show this whole report, or I have to show you the video of this turning or moving around. So for that, sir, like if you want that, then I can just screen record that and send you that as well, sir. Thank you, sir.